Welcome to lecture 55. This is on the extraction of parameters from the DEM. This is a very important lecture in the sense that here we will use the external parameter in the GIS, which is the digital elevation model, and then try to extract different parameters which could be used for various application. And some of the use of the DEM parameters you will learn in the subsequent lecture when I explain the application part. So let's begin the lecture. We know that the digital elevation model is basically the representation of the ground in the third dimension, and each point on the digital elevation model has a coordinate system associated with it along with its height. So you can see that in the picture here there is a digital elevation model and different colors are representing the different heights, and each of the point here, each of the pixel here is tagged or geo reference to the coordinate system. So we know the x, y and z of each and every point. So they are representing these digital elevation models are representing the topography of the surface without the trees on it, without the buildings, without the high-rise structures which are present on the surface of the earth. So it's the bare surface of the earth, the topography of the earth it is showing. Now we know that from our previous knowledge here that this we can create a DEM from a variety of the sources. So either we can have contours and contour map and create the DEM from that data, or spot elevation, try to carry out the develop the tin module and carry out the interpolation and create the, or we may have the GPS points with us, and using those GPS points we are creating. The LiDAR data is a very dense kind of a data. We can get very high resolution DEM which could be produced with the LiDAR data. Stereo images, whether the satellite image or the aerial photography can be used to create a 3D model of the area or digital elevation model of the area. So there are different methods. Now what are the applications, why we should actually use this DEM in our GIS based analysis? We can first of all extract various parameters which we are going to learn in this lecture today. For geomorphological applications, we want to model the flow of the water for hydrology or for the mass movement. Then also we required this DEM because the slope is very important here. We want to model the wetness of the slope or create the water index, it is required. Creation of the relief map, the DEM is very important. If you have to create a 3D visualization of the terrain, and this is very important in 3D flight planning and simulation work, it is being used in a very big way. You can create the physical models including the relief maps with the help of the digital elevation model. Now you can rectify, create orthophotos from the aerial photograph or from the satellite image once you have the DEM. You can also apply the terrain corrections of the gravity measurements. You can carry out the analysis of the terrain for geomorphological or physical division of the terrain into the let us say the plain area, the highly undulating area or the moderately sloping area, things like engineering and infrastructure design. The DEM is playing very important role because we must know the topography of the ground where the project is to be commissioned. Line of sight analysis in many projects where which are related to the alignment of any route, any you can say the power line, then here line of sight is very important. Precision farming, forestry, surface analysis, intelligent transportation system, and archaeology. So there are various applications, as you can see, where we require the DEM or the parameters which are extracted from the DEM, and that become one layer, one thematic map in the GIS along with the other data products. So what are the derivatives which we can derive from the DEM in GIS environment? So input to my algorithm is elevation data or the DEM, and then we are deriving several parameters out of that DEM. So those parameters could be slope or aspect. Many water related, hydrological related studies, many engineering projects require actually this parameter. Then it could be a watershed boundary, the outer watershed boundary, how much is the area which is contributing to a river network, that can be computed. Drainage network, stream channels. So one can identify the different drainage network, the drainage density, etc., and the other streams, the first order, second order, third order streams which are joining to the entire drainage network. You can actually ascertain the intervisibility between the 2 points. So for alignment kind of a study, or if you have to design let us say the airport at a particular place, that probably you require much larger visibility to the surrounding areas. So this intervisibility analysis is carried out. We can also determine the volume of the reservoir. So capacity of the reservoir, because this is another big issue where the reservoir are having a lot of sedimentation over a period of time. So we can determine the volume of the reservoir by having the DEMs of the area. Then amount of the material which could be removed from the mining or the digging activity. So if we have DEM at time T1, DEM at time T2, we can actually take the difference of that and can carry out that. The how much is the material which has been removed. Determining the parameters for the hydrological models, and flood hazard mapping and flood protections. We have to take some flood management actions, then this DEM is playing very important role. Now, what are the parameters, what are the parameterization, how we will go once we have the DEM. So you can see on the right side is the digital elevation model. So what we know is the elevation data and its coordinates. So we first of all, in many of these studies which deals with the hydrology, we have to fill the sink in the DEM. Sink are the points which are acting like a bowl, so that we determine the outlet of the water. So in case of a bowl shape, the water will remain within the confined zone also. Then we determine the flow direction, flow accumulation value, we define the stream, we carry out the segmentation, then we identify the catchment. So there are many things one after the another, they are all related to each other when we want to identify the drainage network or the catchment area from the entire digital elevation model. So one of the inputs, very important input to the DEM is a contour. As I told you that you can generate the DEM from the contour. So process could be that if you have a topographical map and you can do the vectorization, scan it and do the vectorization, digitize the contours and use these contours to create the elevation model of the area. But if you have the digital data in the form of the contour, straight away one can use it for creating digital elevation model. Now this is indicating that at different scales we require this DEM to be created, because our scale of map preparation is different depending upon the application, depending upon the project. So we are selecting some kind of a contour interval here, ranging from 0.3 meter to 6 meter contour interval at different scales. So if you are creating the contours from the spot elevation data, then this kind of a table is very important, so that we know if our working scale is 1:6000, then we need those contour interval at least at 1.5 meter. So once we have the data, then we will like to create from the elevation data the slope map. Now, very simple relationship, mathematical relationship is there, that we know how much is the elevation difference between the 2 points and divide by the distance. So, difference in elevation divide by the distance will give me slope. So, here is the example of a 3 by 3 window here, where 9 values are shown. So, we know the grid size, and also we know what are the values associated with each of the coordinate system of the grid. So, we have here the first value 340, and in the last grid shows 320 value, and now we will use the simple algorithm here, difference in the elevation between the 2 points divided by the distance. So, with respect to the central pixel, that is why the 0 is with respect to central pixel, we will try to carry out that exercise for all the 8 surrounding windows, and we will get all the 8 values in the region. So, that is how this computation of the slope is done. So, now each and every pixel has a slope value. Actually, in the earlier methodology, when we were using only the contour and the hard copy data, was that at every point the elevation value was not available. But once you have now digital elevation model, then at each and every grid cell, now you can calculate what is the value of the slope. So, you do not have to take a general value of the slope, but you can take a specific value of the slope. So, this is showing on the left side is the digital elevation model, which is ranging from the different categories are shown, and the slope map which has been created, and this categorization has been made from the elevation data. It has been converted into percentage slope, and different percentages are shown by different colors. So, you can segment them. So, if you want a flatter area, maybe you will like to go for the dark green areas, or those areas which are flatter, because the slope here is between 0 to 9%. So, those are the areas which are mostly preferred for some engineering projects, commissioning the engineering project. But you also know which are the areas giving you high slopes. So, these red areas are those areas which are giving us very high slopes. So, these high slopes areas sometimes they are to be protected from landslides and other protections which are required in those regions. So, one can actually create a map of continually varying shades here. As you can see on the right side, the high slopes areas are shown and the low slopes areas are shown in the region. So, low slopes areas could be preferred for project planning purpose. The aspect is the orientation of the terrain with respect to the north line. So, that is why this is north line is shown here, and the aspect can be divided into 8 categories. The north aspect will be 0. If I talking of the northeast aspect, it will be 45 degree, east will be 90 degree, southeast 135, south 180, southwest 225, west 270, northwest 315, and then the closing will be 360, which is 0 degree. So, we can actually divide the entire compass directions into 8 distinct directions, and we know the angle of that particular direction. So, that we can calculate with our simple relationship here. Once we know the values, and then we can calculate how much is the angle which is made with respect to north. So, this aspect calculation has been done, and they are shown with different colors on the map, and this particular aspect is very important whenever we are talking of forest cover, whenever we are talking of the forest fire, whenever we are talking of the construction. A particular aspect side is related to some kind of activity only. We will find that there are some faces which are exposed to the sun, and there are some faces on the ground of the terrain which are not exposed to the sun. You have a lot of soil moisture there, you have very good vegetation growth also. So, the portion which is more exposed to the sun will have a lot more soil erosion. So, one can correlate the orientation with the various kinds of activities. The flow direction of the water is also very important to us whenever we are talking of any project on the ground, because the water should not stop stagnant at a point. It should flow into the main drainage system. So in order to understand the flow of the water into the proper drainage systems, we again take help of the um, elevation data. This is the LiDAR data, which is shown very high dense. One can see even the streams very clearly. So the direction we are determining, and we can also find out what is the steepest direction out of the 8. So we have 8 different directions where the slope was computed, and out of the 8, which is the steepest direction where the water could flow immediately, will flow to the another cell immediately, that can be located, and that is the flow direction. So this is the 8 directions model from the central cell. This is 8 surrounding cells which are shown by the alphabets 1, 2, 3, 4, 5, 6, 7, 8. These are 8 compass directions. So we'll find out in which direction the water would flow. Naturally, the wherever it is has got the steepest slope, immediately the water would flow out at that. So it is not necessary that in case of a rainfall at the central point, the water will flow in the all the direction. It will immediately flow in one direction wherever the slope is steepest. So we have to calculate the steepest slope. Direction of the steepest slope is very important in hydrological study. So out of the 8 possible directions, which is the steepest slope direction that we can identify, and one would see that here that the flow is taking place from 67 to 48 pixels. So once we carry out this study each pixel by pixel for every pixels, then we have this kind of a flow direction map. This flow direction map is indicating me that if we take the first cell, from first cell where the water would go. So water would go into the cell with the value 332 from the first cell, and then it will go to the cell where the value is written 320, and then from 320 it will go down to 310, and 310 it will go to 305 in the southern direction. So if you see that cell by cell analysis for the entire cell, you will find that ultimately the water is collected at the pixel whose value is 305 from all the surrounding cells. So that means this is the lowest point where all the other points are contributing. The flow would travel from the other cells, and ultimately the flow will be accumulated at this point. So one can find out how much would be the flow available from each of the cell and how much time it will take actually to travel to this point. So these kind of problems are very useful whenever we are talking of the flood management study. The flow accumulations, now how many cells are contributing to that particular cell. So this is indicating, we are keep on adding the cells number. So the cell which is contributing is next to that is 1. So likewise you find that this is a matrix where all the 24 cells are contributing to this particular point. Now you can create, once you have this digital elevation model, and once you have the contributing area, then you can create a drainage network from these flow accumulation value, which I have shown in the previous slide. So you have to select some kind of a threshold value, that above a particular threshold this is a part of the drainage network, and below that particular threshold it is not. So using that kind of a threshold value, one can create a drainage network. So all the blue lines which are shown here, they are selected by creating a threshold in the GIS environment, and you can actually have a kind of a drainage network which has been created, as you can see here, and then you can superimpose onto the DEM and just have the feeling whether the drainage network which is extracted is matching with those shades or not. The darker shades are indicating the areas with the lower elevations. So the drainage network which has been extracted is superimposed, and you can see there's one-to-one match. So that means it has been extracted with a very good accuracy. Then once you have the drainage map, then there are various parameters one can derive from it. One could be like the drainage density map. So drainage density will be the total number of drainage in a particular area divided by the area. So that kind of computations can be done by the software itself, and you can create a drainage density map and can find out which is the area where the drainage density would be higher and which is the area where drainage density is lower. Now this drainage density has been actually related to many other factors. It has been related to erosion, it has been related to the carrying capacity of the river, etc., etc. So it's a very important. Then the hydrologist may be interested in the stream order map. So what is the stream order? Higher the stream order, better is the carrying capacity of the and more the amount of water which is available in that particular region. So one can see here that this is the stream order map which has been created, and this catchment up to 5 order streams, the thick one which is shown black, this is the 5th order stream, has been actually identified in the region. Then finding the watershed. This was really a very typical problem. Manually it was done on a topographical map or on a contour map, and sometimes there was a chances to make a mistake when you are delineating the watershed using the contour as well as the shape of the drainage network. But nowadays with the help of this flow direction database and the DEM, you can use the capability of the software, and you can flag the pixels which are situated at the higher elevations in the area. And if you flag those pixels and those are joined together, that indicates the watershed boundary. So determination of the watershed boundary is quite straightforward nowadays, particularly when the watersheds were very large. So you can see from the previous data itself, the red one is the watershed boundary, which has been actually created by the GIS software, joining pixel by pixel, finding out the points of the higher elevation in the area using the capability of the digital elevation model. So I know now the boundary, watershed boundary. I can find out how much is the area of this particular watershed boundary, or if I have to delineate sub watersheds. If it is a large watershed and I want to delineate further smaller watersheds according to the tributaries of the main river. So there are several tributaries in the area and which are ultimately joining the 5th order stream. So according to the tributaries, according to those side channels, one can carry out the sub watershed analysis. So here the different colors are indicating the different watersheds. So order of the stream is shown, and then the different watersheds. So here 8 watersheds have been delineated by the GIS software. Now this DEM is very useful for floodplain management or management of the flood areas, because the flood, whenever there is a flood in the river, the water level will rise and then ultimately it will spread in both the sides of the river wherever the slope is steepest, convenient for water to spread. So it will spread in those areas very conveniently. So one can see here that the areas where the water has damaged the land and it has spread into the surrounding lands because of the slope which was available to the water pixels. So the water is flowing actually in those areas and creating the damage. The next one is the visibility analysis. So a lot of studies have been carried out where visibility between one point and the another point is very important. If there are 2 towers which are to be installed and communication is required between the 2 towers, we don't want any obstruction in between, then these kind of visibility is very important. As one can see here that if this is the observer positions and this is the section of the ground here, then there are certain portions of the ground which are visible, and there are certain portion of the ground which are not visible to us. So one can see from this diagram, because of the topography of the ground or because the features which are present on the ground, some part is always obstructed, and you cannot see that obstructed part from that particular height, from that particular location. So if we want the maximum visibility, then probably we have to identify the what is the optimal location of the observer, what is the optimal location of the site. So this viewshed analysis has been very useful in the sports activities like skiing also, that when the person is taking a jump from one particular point and reaching to the another point. So you can carry out that how much should be the height of the target according to the topography of the ground and according to the point where we have to reach in order to establish the visibility between the 2 points, so that the point is visible to the next. Now this is a satellite image, and in the satellite image, if you are trying to superimpose your position, so this is the position of the observer. So the point here is showing the position of the observer at that particular location, and which are the areas if you see all around you. So those lines are the line of sight. The observer is looking in these directions. So whether there is a clarity or not, where there is some obstruction. So this green is showing you that the area it is visible to the observer, but red are those areas where the visibility is obstructed either due to the topography or some features which are present on the ground. Now if you like to see aerial view of that, how much area is visible. So one can see that at the center there is a small yellow dot, and this yellow dot indicate that the 1.75 meter is the height of the observer which has been taken at this point, and then from that particular height how much would be the area visible from that, which are the areas obstructed from the vision, which are the areas which a person can see all around. So this kind of a study is also very useful when we want to decide a optimum site for the airport in order to have the maximum visibility. Now there are many applications, many studies where volume computation has become important. So volume of the material, for example, for the civil engineer is important. If there is a heap of material which is lying on the site, how much is the quantity of the material which is available to us. The volume from medical imaging is also very important, and this volume computation one can do with the help of the contours or effectively with the help of the elevation data. So once we have the elevation data at the different depths, then the volume estimation in a given area can be carried out. So this could be either the excavation activity, we want to know how much is the volume, or if there is a material lying in a factory like wheat or wood chips, we like to know how much is the area volume of the material available, or in the road work if we have to do cut and fill analysis, then also the volume of the earthwork is very important to us. Now there are actually trapezium rule, there are some other relationships also, but trapezium rule is most popularly used. Very simple relationship, we determine what is the actually the area between the two contour values at a regular interval, and then we use this formula. So trapezium rule can be used to compute the area. Then site suitability analysis. So this is the for a dam site. If we are selecting a suitable site for the dam, there are many parameters which are required to be studied in GIS integrated, but you can see the slope is also very important here. So in order to have those different parameters, integrate them together into a certain decision rule so that we can find out what is the best site for the dam, slope, geology, soil type, land cover, proximity to river, proximity to roads, etc., etc. But this slope will come from the DEM. So directly we are using DEM and we are using the other data products, then finally we are determining the best site for that. So this is on the DEM. In the 3D, these are the suitable sites for the dam sites along the river. So you can mark them, you can pinpoint, you can find out whether that area of the reservoir would be available at that particular location or not. So you can determine the axis, suitable axis for the dam site on the DEM, which is axis will be the perpendicular to the river course. You can also do the visualization of the terrain in the 3D environment. So this is another important area where we are not determining the parameters from the elevation model, but we will like to visualize the terrain. We will like to create the animation of the terrain. We want to show what are the changes in the terrain with respect to time has taken place, or what are the elevation difference in the terrain, how the terrain looks like. So without visiting the field, without visiting the ground, or without reaching to that particular spot, which is a difficult spot, you can create that simulation, you can create the model. Once you have the 3D, you can superimpose on the top of the satellite image, or you can superimpose the other data so that you can have a proper visualization of the terrain right in the laboratory itself. So when we see that remote sensing data, various data products are used for creating the DEM. So if we see what is the suitability of these remote sensing data when we are creating a DEM. So we have photographic data, LiDAR data, we have the aerial photograph, things, different sources, but for different applications we require different accuracy. We may require very high accuracy, which is less than a meter from the DEM. We may require a low resolution DEM, which is greater than a 5 meter accuracy. So it depends upon our applications, for which applications we are actually doing it. This is indicating that for very high accuracy, which are the data products which are useful, for medium accuracy, which are the data products. So as far as the accuracy is concerned, and down below is the spatial resolution. At what spatial resolution, what kind of a data product could be used. So you will find that if you want very high resolution and you want very high accuracy DEM, then you have to go for the 3D LiDAR data either, or you have to go for the photogrammetric data, stereo data. Now there are accuracy requirements of the DEM for different applications. So we require for some applications some medium accuracy or crude, but there are some applications where we require very high accuracy, which is written. So less than 0.5 meter accuracy could be required for hydrological modeling, for insurance risk and assessment, form layout design. If we want low resolution DEM, so could be application, could be tourism, etc., or it could be a visibility analysis or environmental impact assessment of the area, or we want to carry out the natural assessment. Now the last column shows what is the accuracy required, okay, what you can achieve and what is the accuracy required for each of the projects. So there are some application area where we need very high accuracy DEM, and we have to go for the methods like the LiDAR methods, or maybe you are collecting the data from the total station. But there are where medium accuracy or crude accuracy is required. Maybe one can actually go to some of the sites which you can see global free DEMs. So there are free digital elevation models available for the entire globe. So these are some of the sites, some of the models, GTOPO 30 space shuttle radar topographic mission, which is called SRTM, ASTER global digital elevation model is available, and JAXA Global allows 3D world. So these are some of the sites where one can go and find out the free global digital elevation model, but they are available at ranging from 30-meter to 60-meter and 90-meter resolution. So you will get a crude kind of a name, and there are many studies when the area is very large. These free DEMs which are available to us globally, they are good enough to serve our purpose. So this is all. Thank you very much.